Thank you for the introduction. We're talking about polynomial Excel, variant of the Excel algorithm using Macaulay matrices over polynomial rings. And this is joint work with Momonari Kudo. In this talk, we deal with the MQ program, solving quadratic system over finite fields. And this XL algorithm is known to be one of algorithms solving this MQ program by applying Gaussian elimination on coefficient matrices. And this hybrid XL is an efficient variant of this XL algorithm. And our main result is that we propose an efficient variant of this hybrid XL, and the proposed algorithm is constructed by using matrices over polynomial rings. And first, I'll talk about the XL algorithm and hybrid approach. MQ program is a program solving quadratic systems over FQ, which denotes the finite field with Q elements. And we set these parameters n and m as the number of variables and equations, respectively. And then MQ program can be written like this. Given a quadratic system F composed of m quadratic polynomials from f1 to fm in fq x1 to xn, then we find one solution a1 to an and to fx1 to xn equals zeros. And then some group system based on this MQ program, such as EOV signature schemes, are known to be candidates for post-quantum crypto systems. So analyzing the complexity of solving this MQ program is very important to evaluate the security of such much-varied crypto systems. And then before explaining the Excel algorithm we introduced, this Macaulay matrices. Here, this F denotes order set of polynomials, and this T denotes order set of polynomials. Monomials. Then this coef Fij is defined as the coefficient of Tj in Fi. And then for these sets F and T, we can find Macaulay matrices like this as a matrix or as an m by n matrix over FQ, actually whose ij element is coef Fij. Then in the XL algorithm, we take parameter d for the degree of monomials as input. Then this td denotes the set of monomials with degree lower than or equal to d. And this id denotes the set of products of monomials with degree lower than or equal to d minus 2 and given quadratic polynomials f1 from f1 to fm. Actually, that means that this ID includes some polynomials with degree lower than or equal to d. Then XL algorithm can be written like this. First, we generate the Macaulay matrix with polynomials and monomials with degree lower than or equal to the capital D. And then in the second step, we perform the Gaussian elimination on this matrix. And by doing so, we can transform the matrix into like that form. And from this part, we can obtain equation which includes only the last TD minus the rank of this matrix plus one monomials. Then if we choose parameter D appropriately, then we can obtain this equation as an univariate equation, and it can be easily solved. And actually, in the third step, we solve this univariate equation and then find the values of the other variables. Next about the hybrid approach, and this approach is an approach for using MQ solvers such as Excel more efficiently. And actually, given a quadratic system F and the parameter K, in the first step, we choose K values from A1 to AK randomly. And then in the second step, we substitute these k values for the first k variables from x1 to xk, and then apply MQ solver to solve on the resulting system only with n minus k variables. But in here, in the first step, we choose k values randomly. So in many cases, we cannot find a solution, and then return to step 1 and choose the values and repeat these steps until we find a solution. And to find a solution, we have to repeat these steps for the q to k times. And in the rest of this talk, we call the hybrid approach with XL as HXL. Then I'd like to talk about the proposed algorithm. And we first show our main idea for the proposed algorithm. In HXL, the XL algorithm with a hybrid approach, we first fix k values randomly, and then we perform a Gaussian elimination on the coefficient matrix and iterate these operations until we find a solution. On the other hand, in the proposed algorithm, we consider first applying the Gaussian elimination on the coefficient matrix, and after that, for the smaller non-eliminated part, we fix values of k variables and again apply Gaussian elimination, and only repeat these last two steps until we find a solution. And by doing so, we aimed at reducing the amount of operations required for each iteration. And we want to show this idea more specifically. Here we suppose that these first k variables from x1 to xk are variables to be fixed. And then we generally receive quadratic polynomials as elements of fq x1 to xn. And then we regard these polynomials as elements of this polynomial ring with only n minus k variables from xk plus 1 to xn with coefficients in the polynomial ring fq x1 to xk. Actually, for example, in the case of q equals 7, n equals 3, m equals 3, m equals 3, and k equals 1, when we receive these polynomials from x1 to x3 as elements of x7, xy, z, then we transform these polynomials into like this form as elements of this polynomial ring only with two variables, 1 and 3. Actually, in f1, the coefficient of y is 6x plus 5, and the constant term is 5x squared plus 4x plus 3. And for these polynomials, we generate Macaulay matrix. And actually, this is a matrix. And when you see the indices of columns, indices for columns are monomials in only two variables, y and z, and the elements of this matrix is in the polynomial ring with variable x. And as I said before, we'd like to perform the Gaussian elimination on this matrix, but here we cannot perform the elimination because this matrix is over the polynomial ring. But when we focus on these three blocks, and degree 4 polynomials and degree 4 monomials block, and degree 3 polynomials and degree 3 monomials block, and degree 2 monomials and degree 2 monomials block. These submatrices are only composed by the elements of the base finite field FQ, F7 here. So we can partly perform the Gaussian elimination on these submatrices, and by using these elements, we can eliminate the corresponding columns. And by doing so, we can partly perform the Gaussian elimination on this matrix over the polynomial ring. And we'll give more formal description of the proposed algorithm. We take two parameters d and k as input, and then unlike the case of the XL algorithm, this TD denotes the set of monomials only in n minus k variables with degree d, and similarly, the set of this ID also denotes the set of products of given polynomials and monomials only in n minus k variables. And this PM denotes the Macaulay matrix with degree with polynomials and monomials, degree lower than or equal to D over the polynomial ring SQX1 to XK. And this PMIATB denotes the submatrix of this PM corresponding to degree A polynomials and degree B monomials like this. Then the proposed algorithm polynomial XL, PXL can be written like this. First, we generate the Macaulay matrix over the polynomial ring PM. And then, as I said before, we partly perform the Gaussian elimination, and by doing so, we can transform the Macaulay matrix into like this form. And after that, we only focus on this lower right smaller block. And for this block, in the first step, we fix the values of k variables, and then we perform the Gaussian elimination on this smaller matrix. And after that, we, as in the XLR plain XL algorithm, we solve the univariate equation and then find the values of the other variables, and only repeat these last 3 steps until we find a solution. And this is the details of linearize one step. For each degree D from capital D to 2, we first perform the elimination on this submatrix PMIDTD composed of only elements of the base finite field. And then we perform the same row operations on PMIDTD minus 1 and PMIDTD minus 2. And then by using the leading coefficients of PMIDTD, we eliminate the corresponding columns. And by repeating these operations from degree D to 2, we can partly perform the Gaussian elimination on the matrix, on the PM over the polynomial ring. And finally, we here compare the proposed algorithm with other existing algorithms. We here asymptotically evaluate the time complexity by assuming the semi-irregularity of the given system. And then and actually this table shows the estimation of the number of operations over FQ of these algorithms in the case of Q equals to the Z and M equal N. And actually we here compare this HX hybrid approach with XL and hybrid approach with Wiedemann XL and crossbred and proposed PXL. Then actually you can see that the proposed algorithm is 2 to the 10 or 2 to the 20 times faster in the case of M equal N. Yeah, so that is our result. And finally, we conclude this talk. In this work, we propose a new variant of HXL, and the proposed algorithm is asymptotically more efficient than other algorithms in the case of N equals M. And one of our future works is proposing fast implementation and analyzing its practical efficiency. Thank you very much.
We have time for question. Yeah.
I have 2 questions for you. So first of all, have you tried to break some NQ challenges using PXL? And another question is, have you considered using multiple polynomial rings, not just one, maybe different ones, maybe one with more variables and one with fewer variables, something like this?
Thank you for the question. And for the practical situation, maybe we haven't yet realized the fast implementation, and we think maybe it might be difficult to realize such fast implementation because our proposed algorithm has to utilize the arithmetic over the polynomial ring. But maybe other existing algorithms can be only performed only using the arithmetic over the finite field. So we think it might be difficult. And maybe the second question is about for the case of the number of equation is larger than the number of variables. Okay. Different polynomial means. So sorry, what is the different polynomial? Okay.
So I was wondering, how do you choose K?
Ah.
And once that you choose K, how do you evaluate the complexity of solving one of the subsystems? Which formula are you using? Is it concrete, asymptotic?
We evaluate the complexity by order polynomial and by substituting actual values for parameters. We estimate the number of operations, and the value parameter k is chosen such that to minimize the complexity. Yeah, so we choose the k in which the total complexity has minimal value.
Following on this complexity, how do you, because I'm still don't understand how you get the complexity, because when you evaluate, you have a degree of regularity, number of rows, and so on. So I miss this part in your talk, how you estimate the complexity. And for me, what is kind of the intuition? Why is this, using this approach is better than the state of the art? Maybe the high level idea, why this is, why you get some complexity improvement.
For the Gaussian elimination in the fourth step on this lowerize smaller matrix after fixing some values. But the original existing algorithms, we have to perform the Gaussian elimination on this matrix, this larger matrix for each iteration. So maybe I think that is the advantage of a proposed algorithm compared with existing algorithms.
Okay, so let's thank the speaker again.